All right, so for problem number 6, we've got two spheres hanging at the end of two strings, and the first part of this problem is to just draw a free body diagram for each sphere. So the general forces we know are the force of gravity. There's a string, so that'll give us a tension force. And then we now have learned about an electric force. It tells us that they are suspended and they have an equal amount of positive charge. We also know that they must have like charges because they're separating along the string. And so that force is going to be a repulsive force on each side. And one thing to note about electric forces is that they are an interaction between two charges, and based on Newton's third law, the force of one charge on another is going to be equal and opposite to the force of that charge on the other. So here we've got tension again and mg. So that's part A. The next part is to determine the magnitude of charge Q on each sphere. So here, since we're solving for Q, we're definitely going to use the electric force, which is K Q1 Q2 over R squared. They did tell us here that both spheres have an equal amount of positive charge. So essentially, the Q's can be reduced down to Q squared over R squared. Okay, the only problem is we need to figure out what this is equal to. And so if we were to break down the tension into the X and the Y components, then one thing we can look at is the fact that this theta, maybe I need a thinner line. This theta is the same as this theta right here. So I've got force of tension sine theta, and I've got force of tension cosine theta. Okay, so let's focus on components. So the sum of the forces in the x direction are going to be negative ft sine theta plus kq squared over r squared is equal to 0 because everything is balanced. And so that gives us kq squared over r squared is equal to force of tension sine theta. The problem here is that we have too many unknowns. So if I next go to the components in the y direction, I have another set of balanced forces. I know that ft cos theta plus mass times gravity is also equal to 0. This should be negative because it's pointing downward. And so ft cos theta is equal to mg, and ft is equal to mg over cos theta. So that allows us to plug in this into our tension force, and we end up with kq squared over r squared is equal to mg sine theta over cosine theta. Okay. The other unknown we have is the r squared, and the r squared we can use the Pythagorean theorem since we know that this length is 1.5, and we know the distance r is actually the full distance between the two charges. If I were to just get one side here, which is r over 2, then I can solve for r squared. So in this scenario, I've got sine theta is equal to r over 2. I'm going to call it L for now. which is just r over 2L. And then if I solve for r, I get 2L sine theta. And I'm going to plug that in for my equation here. And let me kind of make room for this. I'll make it in purple. In the end, I end up with kq squared over 4L squared sine squared theta is equal to mg. Sine over cosine is tan theta. So that makes things a little bit cleaner. And then I'm going to isolate the q squared. So I get q squared is equal to 4L squared sine squared theta times mg tan theta over k. And when I take the square root of both sides, I end up with q is equal to 2L sine theta times the square root of mg tan theta over k. And that would give me my charge. I still have to plug in values, but let me kind of clear out some space for that. Okay, so 2 times 1.5 sine of 30 degrees times the square root of, I need to convert to kilograms, so 0.02 kilograms times, you can use 10 here, 9.8, tan of 30 degrees all over 9 times 10 to the 9th, which is your k value. And let me plug that into my calculator. And I end up with Q equals 5.37 coulombs. Sorry, not coulombs. I have times 10 to the negative 6 coulombs. You can also refer to this as 5.37 microcoulombs. It is 5.36 in the answer key, but they use 9.8, we use 10, so either one is fine. For part C, we have to figure out how much charge is lost when charge is dissipated and it decreases its repulsion angle to 20 degrees, which is easy because we have the equation from part B and all we have to do is plug in 20 degrees. So the length still stays the same, sine of 20 this time. The mass still stays the same. Gravity, we're going to keep it 10 again. Let me just step this down. Tan of 20 degrees all over 9 times 10 to the 9th. Q is equal to 2.91, or let's call it 2.92 times 10 to the negative 6. So that's going to be my charge after some charge is dissipated. It's now at 20 degrees, but we still need the difference. So I'm going to subtract my 5.37 times 10 to the negative 6 from that, and that'll give us our difference, which is 2.45 times 10 to the negative 6 coulombs, or 2.45 microcoulombs. So read the question carefully. It's not just asking for what the charge is, but how much charge has been lost. In the answer key, it says 2.46, which would be if you use 9.8 instead of 10. Okay, so for part D, it says, if one of the strings is cut, find the instantaneous acceleration of the sphere that was hung from this string. Include the magnitude and the direction. So if we look at this scenario, we've got the electric force and the gravitational force pulling down. The tension force is no longer there. And if we were to find the net force, this is Newton's second law, we can solve for the acceleration. Now, the normal way I would do it is if I had an electric force, I could shift the gravitational force so that the vectors are tip to tail, and then I would get my net force right here. And that would require taking the square root of the electric force squared plus the gravitational force squared, which is fine. We can do that, and then we can solve for that solution equal to MA and solve for A, but it is a lot easier to use a different method, which was introduced to me by a student. They mentioned if everything is balanced, then the tension force that is pointing upward in this direction should be equal to the net force that is pulling down. So I'll draw it in this diagram. This tension force would be equal to the net force once the string is cut, at the instant that it is cut. And so since we already calculated the tension force, that saves us a lot of work, a lot of calculation, and we could set up our mg cos over cos theta equal to MA, because that's our net force. And when I divide the m over, they can cancel out, and my acceleration is g over cosine theta. Which theta are we going to use? Well, since it ended up at 20 degrees after the dissipation, it's going to be 10 over cosine 20, and that gives us 10.6 meters per second squared for part D.